Micromachining processes. Okay. Know that micromachining processes include bulk micromachining, surface micromachining, Liga, S-Liga, and the Liga-like technologies, wafer bonding, and micro EDM, right? Such as actually, the EDM stands for electrical discharge machining, okay, and laser micromachining. Let's start from bulk micromachining. Right, first, definitions. Right, bulk micromachining employs orientation-dependent chemical etches such as EDP, KLH, and hydrazine in conjunction with several etch stop techniques to sculpt microstructures from the silicon substrate. Okay, that's the definition. Actually, is from an NSF report in 1988. Okay, pretty long time ago. In another definition, okay, in bulk micromachining, mechanical structures are created within the confines of a silicon wafer by selectively removing wafer material. Okay, and the third one, bulk micromachining uses chemical or plasma selective etching of silicon wafers with the help of masking films to form micromechanical structures. So simply speaking, bulk micromachining involves the etching of the bulk of the silicon substrate. Okay. So it involves the etching involves the etching of the bulk of silicon substrate. Okay, and this etching can be done either with wet etching or dry etching, and it can be isotropic or anisotropic. The bulk micromachining technologies include HNA, which stands for hydrofluoric acid, nitric acid, and acetic acid. So it's the HNA, right? The acronym of HNA. Okay, like KOH, which is a potassium hydroxide. Okay, EDP, ethylene diamine, and pyrocatol. Right, TMH, tetramethyl ammonium hydroxide. Right, Xena difluoride, and DEEP-RE, deep reactive ion etching. Okay, so we have many bulk micromachining technologies. And let's first discuss HNA, isotropic etching. These two figures compare the etch profiles of isotropic and anisotropic etching. Okay, the left side is isotropic etching. Right, we know the HNA is isotropic etching. I pretty know that isotropic etching. For isotropic etching, the etching proceeds equally in all directions. Okay, it etches vertically, also horizontally. Okay, so we will observe this lateral undercut underneath the masking layer. Okay, we know the top layer is the masking layer. Okay, so for isotropic etching, we will definitely observe this kind of lateral undercut. Okay, and for anisotropic etching, right, it's very different. The etching only proceeds, right, for example, in this case, only proceeds vertically. Okay, so there's no lateral undercut. Okay, and HNA is isotropic etching. Okay, ingredients of HNA, we have just mentioned it briefly. Okay, it's a mixture of hydrofluoric acid (HF), nitric acid, acetic acid, or water. Okay, we know that the acetic acid can be replaced by water. And this is the overall reaction. Okay, and actually we can observe that okay, the acetic acid or water serve as a diluent. Okay, actually they do not participate in the chemical reaction. Okay, only nitric acid and HF participate in the chemical reaction. Okay, and this is a etching mechanism. Okay, nitric acid oxidizes silicon, then HF dissolve silicon oxide. Okay, so silicon is oxidized, then HF dissolves silicon oxide. Okay, we know that HF is a chemical etching, right? People use it to etch glass, which is mainly silicon dioxide. Okay, right. Acetic acid and water serves as a diluent. Okay, please know that acetic acid is a main component of vinegar. Okay, so you should know this actually pretty well. Okay. HNA etching can be characterized by this triangular scale. I believe right, this is the first time for many of you to see this kind of triangular scale. Okay, so I will explain right, in details and explain how to rate this triangular scale. First, every corner or side represents one component, right? So totally we have 3 components. So they are 3 sides. Okay, that's the reason we use this triangular scale. Okay, this side, okay, this side represent weight percentage of HF. Okay, from 0% to 100%. Okay, from 0 to 100%. Okay, so this corner actually, this corner represent 100% of HF. Okay, and this corner represent nitric acid, okay, from 0 to 100%, okay, low concentration of nitric acid, high concentration of nitric acid, okay. The bottom side represent the concentration of diluent, either acetic acid or water, okay, from 0 to 100%, okay. And the second, every point inside the triangle represent a unique recipe. Okay, every point inside this triangle represent a unique recipe. For example, this point. Okay, this point actually represent a recipe which leads to a etch rate of, if we enlarge it, and okay, we can see the etch rate is 33 micrometer per minute. Okay. So every point represent a recipe. And to determine the recipe of one point, we can simply draw 3 lines parallel to the 3 sides of the triangle. Okay. For example, in order to determine the recipe of this node, okay, of this point, we draw 3 lines. Right. This one, and this one. Okay, which are parallel to the 3 sides of the triangle. Okay. Then we can determine the recipe of this node. Okay. For example, for this specific node, we can say HF, the concentration, the weight percentage of HF is what? Approximately 12%, right? And the percentage of nitric acid, okay, is determined from this side, okay, and by reading the scale, we can see nitric acid is about 71%, okay, a little bit over 70%, okay, and finally, the concentration of the diluent, okay, will be, in this case, okay, it's acetic acid, okay. Okay, A, okay, is what? 17%, okay. We know that the sum of these three should be 100%, okay. Total should be 100%, okay. So this is how we determine the recipe of a specific point inside this triangular scale, okay. Then the iso-H curve is a collection of recipes of same H rate, okay. We know that, right, those curves, okay, those curves inside this triangle are called iso-H curve. We know that an iso-H curve is a collection of recipes of the same H rate. Right, that's the reason we call them iso-H curve, okay? For example, this curve, okay? This curve, which is labeled with 33, okay? All the recipe along this curve have the same H rate, which is 33 micrometer per minute, okay? So this is the iso-H curve for this specific H rate, okay? And then we can find many other iso-H curves, okay? And the solid curves represent the iso-H curves for acetic acid, okay? But dashed lines are iso-H curves for water, okay? When we use water as a diluent, okay? So that's the difference between solid curves and dashed curves. Okay. Mask materials, okay, namely material which can be used as the masking layer for HNA etching. Okay. First is a thermal oxide, right? Actually, silicon dioxide. Its etch rate in HNA is 300 to 800 angstrom per minute. Okay, actually pretty high etch rate. That's because HNA contains HF, and we know that HF etches silicon dioxide. Okay, so if we want to use a thermal oxide as a masking layer, it has to be thick enough. Okay. CVD silicon dioxide, right? Chemical vapor deposited silicon dioxide, right? Its etch rate in HNA is very high, 0.5 micron per minute. Okay, so typically we do not use a CVD silicon dioxide as a masking layer for HNA. Okay, its etch rate is too large. ALP CVD silicon dioxide, silicon nitride, right? Low pressure chemical vapor deposition. Later we will discuss this technology. Okay. ALP CVD silicon nitride has a actually very small etch rate in HNA, 10 to 100 angstrom per minute. Okay, so this is actually excellent masking layer. Okay, gold chrome thin film, okay, will peel off after 20 or 30 minutes in HNA. Okay, so if the etch time is less than 20 minutes, okay, gold and chrome thin film can be used as a masking layer. Okay, we know that this chrome layer is used as an adhesion layer between gold and the silicon substrate. Okay, right? Gold is inert, so gold will not be attacked by HNA. Okay, but the adhesion layer will be attacked. Okay, so that's the reason why gold thin film will peel off. Okay. Photoresist. Okay, photoresist cannot withstand HNA. Okay, it will be dissolved almost immediately in HNA. Okay, so we cannot use a photoresist as a masking layer for HNA etching. Okay, so we can say this is no good. Okay, actually this is no good, and this is also no good. Okay. Isotropic etching example. Okay, so in this slide, I'm going to show you one example based on isotropic etching, specifically HNA isotropic etching. Okay, and this example is a gas chromatograph on a 2-inch silicon wafer. Okay, please know that a gas chromatograph is a method to separate gases by taking advantage of their different mobilities in a long capillary column. Okay. Let's see. Okay, let me open a new slide. Okay. So let me briefly explain the operating principle of gas chromatograph. First, we need to have a very long capillary column. Okay. Then we can inject gas mixtures. For example, A, B, C, D. Okay. Mixture of gas A, B, C, and D. Okay. So they are injected into this long capillary column from the left side. Then they travel through this column to the right side. Okay. But they have different mobilities or different travel speed. Okay. So they will arrive at the right side at a different time. Right? For example, okay, B may arrive first, okay, then followed by D, A, C, okay. So this mixture of gas can be separated by taking advantage of their different mobilities inside this long capillary column. Okay, so that's the operating principle of gas chromatograph. Okay, so the key element is a long capillary column. Okay, and in this example, this capillary column is etched by HNA on silicon wafer. Okay, and this column is 200 micron wide, 40 micron deep, and 1.5 meter long. Okay, so we can say that it's a fairly long column. And note that this silicon wafer is only 2 inch. Okay, so the diameter is about 5 centimeters. Okay, right. And this 1.5 meter long column was realized by using this multi-turn, okay, many tons, okay, spiral pattern. Okay, that's how a 1.5 meter long column, okay, was fabricated on a 2-inch diameter silicon wafer. Okay, this figure shows an example of an output of gas chromatograph. Okay, we know that different spikes represent different gases. Okay, So the gases are separated at the other end of the column. Any question? Okay, next let's discuss the anisotropic action of silicon. This figure shows a cross-sectional view of the cavities etched on 100 silicon wafer by anisotropic etching. Okay, please know that as a 100 silicon wafer means that this top surface, okay, the top surface of the silicon wafer is a 100 plane. Okay, right, 100 plane. And we observe that the anisotropic etching, okay, result in cavities with a slanted side wall. Okay, actually this angle is at 54.74 degree, and very small or no undercut. Okay, very small or no lateral undercut. Okay, this is very different from the isotropic etching. Okay, so for this anisotropic etching, the etching only proceeds vertically, not laterally. Okay, and actually on 100 wafer, we can fabricate pyramid shape cavity or V-shape cavity or trench. Okay, so these two are actually topside view. Okay, we view from the top of the wafer. Okay, so that's a anisotropic etching on 100 wafer. Okay, and the bottom figure shows anisotropic etching on 110 wafer. Okay, now 110 wafer means that that's the surface of the wafer. Okay, the surface is a 110 direction or 110 plane. Okay. And we can see that trenches with vertical side walls can be fabricated on 110 wafer by using anisotropic etching. Okay. Right, so how do we predict or understand the anisotropic etching of silicon, single crystal silicon? Right, we just need to follow this simple rule. During anisotropic etching, the slowest etching surface, namely 111 planes, will emerge. Okay. So in silicon crystal, 111 planes are etched very slowly. Or to simplify the discussion, we can assume that 111 planes are not etched at all. Okay, so they serve as a kind of virtual etch stop. The etch will be stopped by 111 planes. Okay, so this is how we understand, how we explain the results, okay, of anisotropic etching in silicon crystal. Okay, then the side walls of the etched structures will be 111 planes. Okay, the side wall. Okay, these two slanted side walls are 111 planes. Okay, right. There's 4 side walls of this pyramid-shaped cavity are 111 planes. Okay, and this vertical side walls are 111 planes. So this is a simple rule to explain the anisotropic etching in single crystal silicon. Okay, now let me explain the anisotropic etching on 100 wafer in more details. Okay. Right, to understand the anisotropic etching on 100 wafer, the key is to find out 111 planes in silicon crystal and how they are related to 100 plane. Right. Please know that we just mentioned that 100 wafer means that its surface is a 100 plane. Okay. So for example, we assume the wafer plane is this plane, and this top plane. Okay, that's a 100 plane. Okay. So how is this plane related to 111 plane? In silicon crystal, we actually have discussed this. This in previous lectures. Okay, in silicon crystal or in this cubic crystal, there are 4 111 planes. Okay, the first is this yellow or orange. Okay, on my screen it's a little bit yellow. Okay, this yellow plane is a 111 plane. Okay, this plane intersects x, y, z axis with equal distance. Right, so 111. Okay, that's the first 111 plane. Okay, I know that here this 111 plane I stand for equivalent 111 planes. Okay, the second plane is this red plane. This plane, the Miller indices of this plane are 1, 1, -1. Okay, so this plane actually intersects x and y with equal distance, and intersects z-axis at its negative direction. Okay, so it actually intersects the negative z-axis. Okay, so that's the reason we have -1 here. Okay, so this red plane is 1, 1, -1. And this green plane is what? 1, -1, 1. Okay, so this plane intersects x and z with equal distance, and intersects negative y-axis. Okay, this is x, this is the y, this is the z. Okay, and the last one, the fourth one, this blue plane is a -1, 1, 1. Okay, so totally 4 111 planes. Okay, so the cavity etched in 100 wafer is bounded by these 4 111 planes. Okay, yellow one, red one, green one, and the blue one. Okay, so as a matter of fact, for this pyramid shape cavity, okay, but it's 4 side walls. Okay, 1, 2, 3, 4 are these 4 111 planes. Okay, right, 1, 2, 3, 4. Okay, totally 4 side walls and 4 111 planes. Okay, and right, the edge will be stopped by these 111 planes. Okay, they serve as a virtual edge stop. But in addition, just a moment. Any questions?
Yes, Professor. So for this 4 111 planes that you had explained in the first cube, when we see the 1 1 -1 So it is intersecting z at 0, is it? How is it intersecting?
Very good question. Yeah, I think I understand your question. Okay, just a moment. Let me share the screen again. Okay.
Sure.
Let's see. Oh, okay. I need to find a Zoom first. That's a very good question. Okay. Okay, so it looks like this red plane intersects z-axis at 0, right? But actually, we can move it in a parallel way. You see, for example, this one. Okay, let me change the color. Red one. Let me change to red color. You see, this plane is a parallel to this red one. Okay. Then it intersects x and y with equal distance, but intersects the negative z-axis. Can you visualize that in your mind? And the two parallel planes have the same Miller indices. So these two planes are the same plane. Okay.
Okay.
So I wish that answered your question, right? Because in order to get the Miller indices, we have to find the intercepts of the plane on the x, y, z axis. Okay. But for this red one, it actually cut through the origin, right? So actually, we are not able to find the Miller indices. Okay. So we have to move it parallelly. Okay, and find the Miller indices of this one, and that will give us the 1, 1, -1. Okay.
Okay, perfect. Thank you.
Very good. The angle. Okay, next the angle between 1, 1, 1 plane and 1, 0, 0 plane. Okay. In the slide, okay, we mentioned that the slanted sidewall and the top surface had an angle of 54.74 degrees. Okay, namely, okay, we know that this is this plane is a 1, 1, 1 plane. Okay, the angle between 1, 1, 1 plane and the top surface 1, 0, 0 plane is 54.74 degrees. Okay, how do we calculate this angle? Okay, so why is this angle 54.74 degrees? Okay, we can calculate this angle using two methods. First one is called the cubic method. Okay, based on this cube. Okay, but this shaded plane is a 1, 1, 1 plane. Okay, and this top plane is a 1, 0, 0 plane. Okay, and the angle between them can be calculated using this triangle, this green triangle. Okay, and then we can take out this triangle from this cube. Okay, so we laid in a 2D plane. Okay, this side is this side, right? The edge of the cube. Okay, so its distance is a, and this side is a half of this diagonal distance. So this distance is a square root of 2 divided by 2 times a. Okay. Then this angle, okay, let's call this angle theta. Okay. Then tangent theta will be equal to this distance divided by this distance, right? So a over square root of 2 over 2a. So it's equal to square root of 2. So theta is equal to arctangent square root of 2, which will give us 54.74 degrees. Okay, so you can verify this calculation by yourself using a calculator. Okay. So this is the cubic method. The second method is based on vectors. I believe everybody knows how to perform this dot production, right? The dot production of vectors. Right? If we have two vectors, right, vector A and vector B, okay, this is vector A, this is vector B, okay. Then the dot production A dot B is equal to the length of A times the length of B times cosine theta, right? Theta is the angle between the two vectors. Okay, so cosine theta will be equal to A dot B divided by the length of A and the length of B. Okay, so then theta can be calculated by arc cosine. Okay, and then in our case, okay, we want to calculate the angle between 111 plane and the 100 plane. Okay, so vector A is 100, okay, which is perpendicular to 100 plane. Okay, right. So the vector is 100. Okay, and the vector B is 111. Okay, which is perpendicular to 111 plane. Okay, then A dot B is equal to what? A dot B is equal to 1 times 1 plus 0 times 1 plus 0 times 1, right? So it's simply equal to 1. Okay. So cosine theta. Okay, let me use this space. Cosine theta is equal to 1 divided by what? The length of A is 1. The length of B is what? Square root of 3. So theta should be equal to arc cosine 1 over square root of 3. And then if you use a calculator, you can easily find out that this theta should be equal to 54.74 degree as well. Okay. So we can use this vector method to calculate the angle between 111 plane and the 100 plane. Okay. Questions? Okay, now let's summarize anisotropic etching on 100 wafer. Okay. Let's first consider we have a rectangular mask or rectangular opening. Okay, with the edges perfectly aligned to 110 directions. Well, why do we have to have this requirement? Right. In this slide, we learned that, okay, I guess I missed this point, okay. The intersection lines between the cavity and the 100 plane, this top plane, are 110 directions, okay. Namely, the intersection line between 111 plane, okay, and the 100 plane, the top surface, are 110 direction, okay. This diagonal direction is right, 110, okay. This is also 110, right? So 100 directions are the intersection, okay, intersection lines between 111 plane and 100 plane, okay. Those are 110 directions. But if this rectangular mask has all its edges, okay, 4 edges, perfectly aligned to 110 direction. This means that the edges, the 4 edges, actually are perfectly aligned to 111 planes. Okay, so then after we start a nisotropic etching, right, those 4 111 planes will emerge immediately. Okay, so after etching for a while, there's a rectangular mask or rectangular opening results in a cavity with 4 slanted side walls formed by 111 planes. As I said, okay, 111 planes are virtual stopped, okay, in anisotropic etching, okay. They will stop the etching, so they will emerge, okay. And this is a cross-sectional view of this cavity, okay. The side walls are slanted side walls are 111 plane, okay, and the angle is 54.74 degree, okay. Questions? If we continue etching, what will happen? We know that, right, this 2, okay, let's focus on this cross-sectional view, okay. Well, these 2 planes are 111 planes, right? So they will not be etched. The etch will only proceed vertically, right? Vertical direction. So eventually, what will happen? Eventually, right, these 2 111 planes will meet with each other. Okay. Or we can see that the 2 111 planes on the long sides meet with each other, and then eventually we obtain a V groove. Okay, right. This is a cross-sectional view along AA, along this line. Okay, and the bottom is a cross-sectional view along BB. Okay, along this line. Okay, so this cross-sectional view is a V shape. Okay, so we call this a V groove. Okay, and it's also called self-terminated V groove. Why do we call it self-terminated? If we still continue the etching, what will happen to this V-shaped cavity or V-shaped channel? Nothing will happen, right? Because now this structure is completely bounded by 4 111 planes. Okay, and the 111 planes serves as a edge stop. So edge will be stopped. Okay, so even if you continue etching, this V shape will not change. Okay, so we call this self-terminated. Okay, the edge will be terminated. Okay, it will be self-terminated. Okay. Any question? Okay, next, let's consider the case with a U-shaped opening. Okay, so now the mask is a U-shaped opening. Okay. Initially, okay, after etching for a short period of time, we will observe a U-shaped shallow change with the side walls bounded by 1, 1, 1 planes. So all those side walls are 1, 1, 1 planes. Okay. Then we observe, right, these two convex corners. Right, what is a convex corner? Actually, very simple. Right, if this angle is greater than 180 degrees, then it's called convex corner. Okay. On the other hand, this kind of angle, right, which is less than 180 degrees, is called concave. Okay, concave angle. Okay, or corner. Okay. Then the convex corners, okay, where 1, 1, 1 plane meet are not stable. Okay, we know that by these two planes, okay, this plane and this plane are both 1, 1, 1 plane. Okay, so this convex corner is where these two 1, 1, 1 plane meet. Okay, and this convex corner is not stable. Okay, so these two convex corners will be rapidly undercut. They will be attacked. Okay, they will be edged. And this allows the creation of suspended structure. Right? For example, cantilever beam. Okay, so this masking layer becomes freestanding or a cantilever beam. Why is a convex corner unstable? Let me give you a simple explanation, a kind of superficial explanation. Okay. Previously we mentioned that 1, 1, 1 plane, okay, are not edged, okay, by anisotropic etching. Okay. But that's only true if the etching is from the front. Okay, so if the etching attacks 1, 1, 1 plane from the front, 1, 1, 1 plane will not be edged. However, right, 1, 1, 1 plane can be attacked from the side. Okay, and for this convex corner, okay, 1, 1, 1 planes are not well protected from the side. Okay, for example, for this vertical 1, 1 plane, where the etching can this can be attacked from the top. Okay, and for this horizontal one, it can be attacked from the right. Okay, so they can be undercut or they can be edged. Okay, and it's very different from the concave corner, where the two 1, 1, 1 planes protect each other's side wall. Okay, so concave corner is stable. Okay, convex corner is not stable, so it will not last long in anisotropic etching. Okay, it will be undercut quickly. This slide shows a 3D illustration of the convex corner undercut. Okay, so we still have a kind of U-shaped opening. Right? Initially, we observe this U-shaped shallow change. Okay, and all the side walls are 1, 1, 1 planes. Okay, and these two convex corners. Okay, and these convex corners are not stable, so they can be undercut. And after the undercut starts, the exposed planes are not 111 planes anymore, okay? And will be quickly edged, okay? For example, in this case, actually 411 plane, okay? 411 plane is exposed, okay? Which will be, this plane will be edged quickly. When will the undercut stop? It will stop when this 111 plane is reached. Okay, the 111 plane on the back is reached. Then the convex corner disappeared, and the undercut will be stopped. Okay, so this is the final structure. Okay, the final structure will be bounded by 111 planes with concave corners. Okay, no convex corner. Okay, and this give us a suspended beam or freestanding cantilever beam. Okay. And this is an SEM image of two cantilever beams fabricated using this method. Okay, based on convex corner undercut. Okay, and this wall, this side wall actually is a 111 plane. Okay, so the undercut is stopped by 111 plane. Okay, now let's consider this question. Okay, what will happen if the edges of the rectangular mask are not perfectly aligned to 110 direction? Okay, I know that 110 direction is an intersection of 111 plane and 100 plane. Okay, by this direction. Okay, this is a 111 plane. Okay, so it intersects the top 100 plane along this 110 direction. And in the silicon wafer, okay, there is a major flat. Okay, the major flat is 110 direction. Okay, so what if this rectangular opening is not perfectly aligned to this major flat, namely 110 direction? What will happen? Okay, let me enlarge it. Will we get a cavity with four slanted side wall like this one? Or the question is, are these four side walls 111 planes? They are not, right? They are not 111 planes, right? Because the edges are not perfectly aligned to 110 direction. So where are the 111 planes? Or where are the nearest 111 planes? So right here. This line is parallel to the major flat. Okay. Oh, shorter. Okay. So actually the opening, the final opening will be the smallest rectangle that encloses this original mask. Okay, and its edges, its four edges are aligned to 110 direction. Okay, because those are the nearest. Okay, those four planes are the nearest 111 planes. Make sense? Okay. Now, what if we have a opening with an arbitrary shape? Okay, like this one. What is the shape of the opening after etching long enough? Again, please note that the edge cavity will be bounded by the four nearest 111 planes. Okay, so the opening will still be the smallest rectangle that encloses this opening. Smallest. Okay. A smallest rectangle that encloses the original mask with its four edges aligned to 110 direction. Okay, that's what we end up with eventually. Okay, for an arbitrary opening. Okay. Any question? Okay, so that's an isotropic etching on 100 wafer. Okay. Next, let's briefly discuss an isotropic etching on 110 wafer. Okay, but please know that 110 wafer means the surface of the wafer is a 110 plane. Okay, namely this plane, right? This one. Okay, this plane, which is parallel to z-axis and intersect x and the y-axis with equal distance. So its Miller indices are 110. Okay, so it's parallel to z. Okay, so index of z is 0. Okay. Again, we have 4 111 planes. Okay, so we need to find out their relationship. Okay, to 110 plane. Right, this plane parallel to z-axis. Okay, and the first 111 plane. Okay, 1, -1, 1. Okay, which intersects x and z with equal distance, and intersects the negative y-axis, right? So -1 here. Okay, this plane is actually perpendicular to 110 plane. Okay, perpendicular. Similarly, okay, -1, 1, 1. Okay, right? This 111 plane. Okay, which cuts negative x-axis and intersects y and z with equal distance. Okay, this plane is also perpendicular to 110 plane. Okay, right. And the other two, 111 and 111 -1, okay, are not perpendicular to 110 plane. Okay, so two perpendicular ones, right? The other two are not perpendicular. Okay, so by taking advantage of these two perpendicular ones, we can fabricate trenches with vertical side walls on 110 wafer. Okay, trench with the vertical side wall. The vertical side walls are either -1, 1, 1, or 1, -1, 1. Okay. Right. Quick question. Are we able to fabricate trenches with the vertical side walls on 100 wafer using wet anisotropic etching? No, we cannot, right? Because none of the 4 111 planes is perpendicular to 100 plane. Okay, right? These 4 111 planes all intersect 100 plane with the angle actually not equal to 90 degrees. Okay, so actually we cannot using wet anisotropic etching to fabricate trenches with vertical side walls on 100 wafer. Okay, that's determined by the crystal plane. Okay. And in addition, we can also fabricate trenches with or not trenches with vertical side wall, okay, or V-shaped trench, okay, with a slanted side wall, okay, on 110 wafer, okay. But please know that we are able to fabricate V grooves on 100 wafer as well, okay. And we can calculate this angle, right? This angle will be equal to what? 180 degree minus 2 times 54.7, right? Okay, that's the theta of this angle, okay, of the V groove fabricated on 100 wafer, okay. We can also fabricate V grooves on 110 wafer. However, the angle will be different, okay. Actually, the calculation of this angle is as shown in this slide, okay. Please note that we skip this one, okay. Don't worry about this slide, okay. Let's go to the next one, okay. The calculation of this angle theta, okay. The angle of the V groove on 110 wafer, okay. Right. This angle is simply the angle between these two 111 planes, right? Okay. And then we can use this rectangle, okay. This rectangle to calculate theta, okay. Right. And this distance is A, okay. This vertical distance is A, okay. It's the length of the, no, it's a cubic edge, okay. And this distance is half of the diagonal distance, okay. So square root of 2 over 2a, okay. And these two lines represent the two 111 plane, okay. So this angle, okay, is equal to theta over 2, right? That's theta over 2, and the tangent theta over 2 is equal to this distance a divided by this distance, square root of 2 divided by 2 times a, okay. So tangent theta over 2 is equal to square root of 2. And the theta is equal to 2 times f tangent square root of 2, which is 109.47 degree, okay. So this angle, okay, is different from the angle in 100 wafer, okay. So we can fabricate V grooves on both 100 wafer and 100 and 110, okay, but they have different angle. Questions? Okay, we still have some time. Okay, let's continue. Okay, let's finish by in 10 minutes. Okay, last 10 minutes. Okay, next, let's discuss some specific anisotropic etching. Okay, the first one is called EDP. Okay, that's an acronym for ethylene diamine pyrocatical and water. Okay, so EDP. Okay, and it's also called EPW. Okay, where W stands for water. Okay, and this is a chemical reaction, and we can observe that. Okay, hydrogen gases are generated. Okay, so you will observe bubbles on the silicon surface. Okay, advantages of EDP: excellent boron edge stop performance. Right, later we will explain what is a boron edge stop. Okay, yeah, but EDP has excellent boron edge stop performance. Wide range of etching rate from 10 to 100 micron per hour. Low silicon dioxide etch rate. Okay, so silicon dioxide can be used as a etching mask. Chrome gold can also be used as a masking material. Disadvantages: carcinogenic, which means what? EDP can lead to cancer, can cause cancer. Okay, so this is very bad. Okay, so that's the reason EDP is not very popular at this moment. Okay, because it's carcinogenic. Okay, the only reason that some people are still using EDP is to take advantage of its excellent boron edge stop performance. Okay, that's probably the only reason that some people, okay, are still using EDP. Okay, otherwise, everybody want to avoid EDP, okay, because it's carcinogenic. Okay, and another disadvantage is its aging problem when it's exposed to air. Okay, especially oxygen. Okay, so it is associated with some aging issue. Okay, namely the etching rate may vary, okay, may change or decrease, okay, in air. This table summarizes some recipes, EDP recipes. BH, FH, SH. B is the basic recipe. Okay, F is basically means a fast etch. Okay, so it has a higher etch rate. Okay, compared to BH. SH is a slow etch. Okay, so its etch rate is very small. Okay. Okay, the second anisotropic etchant is KOH, potassium hydroxide. Okay, 20 to 50%. Okay. Advantages of KOH: very high 100 to 111 etch ratio. Okay, as high as 400. Okay. So this means if 100 plane is etched by just a moment. Okay. The PowerPoint is doing some operation, saving whatever, which prevent me from doing anything. Okay, let's see if we can recover. Okay. So this H ratio, okay, 400 basically means if 100 plane is etched by 400 micron, 111 plane, okay, is only etched by what? 1 micron, okay. So this H is very anisotropic, okay. The ratio is 400 to 1, okay. So this leads to small undercut underneath the mask layer, okay. Very small undercut, okay. And the 110 over 111 H ratio is even higher, for 500, okay, even higher, okay. So this leads to deep vertical trenches on 110 wafer, okay. And its QH is relatively safe, okay. It's a non-carcinogenic, okay. So it's much more widely used, okay, than EDP. Disadvantage: high silicon dioxide etch rate. Okay, so if you use a silicon dioxide as a mask layer for KOH, this layer needs to be thick enough. Okay. And another disadvantage is a poor boron edge stop performance. Okay. So it's a boron edge stop performance is not as good as EDP. Okay, EDP has excellent boron edge stop performance. Right. So if you want to choose a etchant that will use a boron edge stop, which one do you choose, KOH or EDP? Right. Typically, we choose EDP, okay, because EDP has a much better boron edge stop performance. Okay. I think I will stop here for today.